I'm Charles Wilson, Staff Product Cybersecurity Architect at Torque Robotics. This presentation will cover secure settings. This diagram shows the overall AVCDL training path. If you're taking this training, it's assumed that you've already completed the AVCDL overview training, and additionally, that you've completed the Requirements Taxonomy, Security Requirements, Secure Design Principles, and Apply Secure Design. This training will cover secure settings. It's well appreciated that in order to create something as complex as a symphony, that there's going to be a large number of instruments at play. There are going to be individuals who are highly skilled at what they do. There's going to be a large amount of coordination in order to be able to create the final result, just like we see here with the London Symphony Orchestra at Abbey Road Studios. Less appreciated is the fact that behind the scenes, there is a tremendous amount of tuning and configuration that goes on in order to take the material that's produced and get the most out of it. Similarly, when we produce a highly complex system, we use compilers, static analyzers, fuzz testers, linters, and dynamic analysis tools to ensure the system's cybersecurity. Each of these tools has a collection of settings used to temper the tool to produce specific types of output and provide specific information and instrumentation of the code that it's being applied to. And some of these settings are relevant within the context of cybersecurity. It's important that we know what those settings are, what the trade-offs in using those settings are, and ensure that we document them appropriately so we have both reproducibility and can make assertions about how cybersecurity engineering is being addressed within the system itself. It's also important to realize that once identified, these settings won't necessarily be used, and that even the ones selected for use may not be applied to all elements within a system. Let's get into it. First, we're going to look at the workflow that's involved in the secure settings process, and then examine each of the activities it contains. Our workflow for determining the secure settings is broken down into 4 discrete activities. These are identifying the options relevant to security, categorizing those options, selecting which ones we're going to use for each element, and finally, applying those options to the build system. Our first 2 activities are performed on a per-tool basis, which is to say that we can look at those without having to concern ourselves with the actual system that we're going to apply them to. The first thing we need to ask ourselves is, what are security-relevant tools? These include things like linters, compilers, static analyzers, fuzz testers, and dynamic analyzers. This is not to say that this is everything, but these are the type of tools that we focus on when we're looking at settings within the context of cybersecurity. For each tool used, we're going to identify what cybersecurity-relevant options are available. Amazingly, cybersecurity options tend not to be the focus of the documentation for most tools. And because of this, it's sort of a treasure hunt to determine what the cybersecurity-relevant options are. The places that you're going to be looking for this information are hard copy documentation, if any exists, online references, and in some cases, the source code for the tool itself. The cybersecurity SME is going to take this documentation and create a tool security options document that identifies all of the options that are available within the cybersecurity realm for that tool. This list will contain a 4-tuple of information containing the option itself, a description of the option, the relevance of the option in the cybersecurity context, and the class of the option. Now let's consider what we mean by class. When we talk about class, we're specifically talking about NIST Bug Classes. In 2024, NIST released SP 800-231, the bug framework. This is intended at formalizing cybersecurity weaknesses and vulnerabilities. There are 3 broad categories of bugs, and these are input, memory, and data. In the input category, we have validation bugs and verification bugs. In the memory category, we have addressing bugs, management bugs, and use bugs. Finally, in the data category, we have declaration bugs, name resolution bugs, type computation bugs, and finally, type conversion bugs. By assigning a class to each of the options, it more readily allows us to identify where the particular setting is applicable. And also, further down the line, we're going to be able to use that information for winnowing down which options we're going to apply. With the tool security options list in hand, we can go about categorizing our options. As a reminder, we have the option, description, relevance, and class to work with. Again, this is something that the security SME is doing. Our categorization will be added to the current 4, and a categorization security options report is generated. The question now becomes, what's a category? Why do we have it? And what do we do with it? Given infinite time and resources, we could decide to use every cybersecurity option available. Now, of course, we don't have either infinite time or infinite resources, so we need to categorize the options and decide how best to prioritize them. We could separate them into any number of buckets. We could use a low, medium, high categorization where we're going to commit to always doing the high ones. We're going to do the medium ones where necessary and the low ones when time and resources permit. The problem with this type of categorization is that it's fairly open to interpretation as to whether medium is really on the high side or the low side. This makes working with a multi-bucket approach difficult. So what we can do is look to the way we address issues in general through the use of a bug bar where we establish a threshold, dividing things into only 2 buckets. If we approach it this way, then what we have are things that we may do and those that we must do. This is a much more realistic approach in practice. Regardless of how many buckets you create, you must categorize the options. Remember that you also have to document why the categorization exists. It can't simply be that you looked at something and thought it was a high, or you thought that it was a must-do. You have to make a decision that is going to be supportable. So if your must-do list says that you have to fix all memory addressing bugs, great. That makes it a must-do. Versus you may deal with name resolution bugs, or you may deal with type conversion bugs. Whatever you choose, you have to have a consistent, supportable rationale that is reproducible. It's important that the replacement of a tool doesn't render all these previous efforts useless. Once the cybersecurity settings for these tools have been determined, they can just sit there until you're ready to use them. But it's important to consider that it's unlikely that the settings are going to be used uniformly across every element within the system. So let's look at the final 2 activities and see how we're going to approach these per element considerations. With the categorized tool security options in hand, we can now look at individual elements. The cybersecurity SME needs to be working with the development SME on this because every element has its own particular set of circumstances. And our intent here is to utilize all of the information that we have, and that's the option, its description, its cybersecurity relevance, its bug class, input memory or data, and its category to ensure that we focus on what's important. We're going to look at each and decide which ones are applicable to the element. That gives us a set of element-specific tool cybersecurity options. This list extends the information we already have by adding the disposition for each option. Keep in mind that the disposition needs to include an explanation when an option is not used, even though it's been categorized as needing to be used. And finally, we generate a security options qualifications report that provides a human-readable form of the results of this activity. Now you might ask how the element could possibly impact whether we use those options already identified as necessary. Let's take the case where you're looking at the compiler options, and you're looking at a particular warning setting that's been identified as being necessary. It may well be the case that you're using third-party libraries or headers. These are things that you don't have control over. And so if you apply that warning, you're going to get issues that can't be addressed. This is just a reality. This is not to say that there aren't actual issues present, however. Should it be decided that you would like to look at the library and analyze it, that's fine. Should it be the case that you'd like to go to the vendor and say, we want to make sure that this class of issue has been dealt with, that's something that belongs in the cybersecurity interface agreement. Having your categorized tool security options documented is useful because that information can be given to the third-party vendor. However, in many cases, you're going to be dealing with compiler-related materials which are not compatible with these settings, and they're just going to generate a ton of issues. And so you have to work with what these limitations are. There may also be timing-related considerations. This is something we're going to see in a static analysis context because every checker is run separately. Because of that, you want to be judicious with which ones you select so you don't make the analysis time unwieldy. These are the considerations that you have as you're selecting the security options to be applied to a given element. Once we have the element-specific tool security options, our next activity is to apply those options. This is a task that is typically done by the DevOps SME, who owns the build system. We're going to take the build file and the element-specific cybersecurity options and apply the identified options, yielding an updated build file. This closes the loop in terms of going from possible security options to actually implemented security options. It's important to consider that once security options have been turned on, that there should be an expectation of an increase in identified issues. It's important to communicate that these changes are coming, and it's recommended to dry run these settings to see what you're going to be in for when they're actually brought online. That's the process that we're going to use in establishing what secure settings for each of the tools and each of the elements that are going to be utilizing those tools are going to be. Now let's review what's been covered. To summarize, our process is to first identify the cybersecurity options that are available, then to categorize those options so we'll know which ones we're going to focus on. Next, we're going to select those options which are appropriate to each element that the tool is going to be applied to. We're going to make sure that we record the options that have been selected so we know why we're doing these things and why we're not doing them. Finally, we're going to put those options into effect. For additional information and to get a more in-depth set of references, the Secure Settings document, secondary document, is available in the AVCDL GitHub repository. All AVCDL material, both in source and distribution forms, are available on our GitHub site, as shown here. Because of the size of the repository, it's recommended that you either clone the repository or download a zip archive of it if you're not familiar with using Git. Instructions for downloading a zip archive are linked to on the repository's front page. Videos covering various aspects of the AVCDL are available on our YouTube channel, as shown here. It's important to note that all AVCDL materials, except for the introductory blog posts, are intended for product cybersecurity engineering practitioners. With this training complete, you can proceed to the other training at this level, Secure Design Review. Additionally, if you've completed Threat Prioritization, you can also proceed to Attack Surface Analysis, Threat Modeling, Penetration Testing, and Vulnerability Identification. Additionally, you can proceed to either Code Reuse or Secure Coding. Here are the references to the source material used in the creation of this presentation. They'll also be included in the video description. Additionally, this presentation source material will be provided on the AVCDL GitHub repository.